Hello students, welcome back. In the previous lesson, we went through something really important. That is, given linear map, how to find the matrix associated to it. Let's see. No, not this one. This one. Basically, we need the column vectors. So E1 is going to 1, 1, 2. That's going to be a column. And E2 is going to negative 1, 3, 4. That's going to be the second column. And put those together, then that's the matrix associated to this linear map, like this. Column, and then next column. Here's another example. E1 is going to cosine, comma, sine, and E2 is going to negative sine, cosine. We have column and then column. In general, we have this kind of expression. First column, second column, dot, 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 in the end, the last column, like this. And let's see. V1, V2, all the way up to Vn are sent to L of V1, L of V2, L of V3, all the way up to L of Vn, but those coordinates are y1, y2, y3, all the way to yn, and those go to columns. Okay, that's a formula, and that is going to be far more important for most of the students. But still, let's talk about the proof. Now, I don't think you'll have to reproduce this proof out of nowhere. So if you do not follow everything, that's going to be okay. But this scheme, getting columns, 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 that's something everybody has to remember in case you end up with some example problems like these. Okay, let's begin the proof. Let y1, y2, y3 all the way up to yn be those columns, the coordinates of the basis vectors, L of V1, L of V2, L of V3, all the way to L of Vn. And in order to see this better, I did the color coding like this. And now, if you have different bases, then you have different coordinates. So it is important that you have a set basis here, and the set basis is W1, W2, all the way up to Wm. And then we just define the matrix as the columns. Y1, Y2, Y3, all the way to Yn. See the color coding? Just the columns. And then we do some brute force computation. Get arbitrary v, then that v can be written as x1 v1 plus x2 v2, x3 v3, all the way up to xn vn, because v1 through vn generate the vector space v, and also this coordinate expression x1, x2, x3, x4, all the way to xn, that expression is unique because this is basis. This is basis. So the existence of this linear combination comes from the generating, and the uniqueness is actually coming from the linear independence. In any case, we have the unique expression. Now what do? We simply put those into L of V and do some brute force computation basically. And then what do? We can separate each linear combination, x1 L of V2 plus x2 L of V2, x3 L of V3, and so on, all the way up to xn L of Vn. And then, what is L of V1? We have this coordinate expression as columns. So A11, A21, A31, all the way to AM1, those are the coefficients, or those are the coefficient of linear combination based upon the spaces. In other words, why did I lose this alignment here? Okay, So L of V1 is actually A11W1, A21W2, A31W3 all the way up to AM1WM. You see this column? And then same goes to the second column. L of V2 is equal to A12W1, A22W2, A32, A42 all the way up to AM2WM. You see, the linear combinations go to columns. Let's do this again. The last count, A1n, A2n, all the way to AMN. Look at this last column. And these are coefficients, or the coordinates of those. So what do we have? A1nW1, A2nW2, all the way up to AMNWM. And then what are those x1, x2, x3, all the way up to xn? Those used to be there before, which eventually came from the coordinate expression of V. Okay, now let's do a bit of an algebra here. And instead of getting all those x's and then all those w expressions, let's switch order and then let's get all those w's together and then, well, rearrange the additions, scalar multiplication basically, and we get this expression, A11x1, A12x2, all the way up to A1n xn. Basically, first, like this, and then second, and second, all the way up to second, and mth, all the way up to mth, like this. So W1, W2, all the way up to Wm expression. And let this be Y1, and let that be Y2, and this is Ym. And then we just compare. Y1, Y2, Y3, all the way to Ym in column happens to be the same as this matrix multiplication. So were you able to follow all this computation? Well, it was tricky, but in any case, please remember the end result. I don't think I'll ever write a problem that asks you to reproduce this proof out of scratch, but the end result, the conclusion, how to get this matrix associated to a given linear map, we just get the basis, V1, V2, V3, all the way up to Vn, and then get their images, L of V1, L of V2, L of V3, and so on, and express those in column. Let's see, if we went through examples before, is there some more example? Okay, all right. And some example we went through before, but let's look at this again in an alternative viewpoint. Okay, here E1 is going to 1, 0. E2 is going to 0, 1. And basically they're staying the same. So of course this is identity, but that's a bit too trivial, isn't it? Because you see, after all, this is an identity map, so too trivial. Let's go to the next one. Okay, this is a little bit better. E1 is going to A, 0. Come on. And E2 is going to 0, B. Basically, this is happening here. E1, let's see, okay. E1, which is equivalent to 1, 0, is sent to A0, A0. And E2, basically 1, 0, is sent to 0b. So that's basically it. So 1, 0 multiplied by a, so it's a stretching by factor of a if a is greater than 1. And this 1, 0, 1 times b, so we get 0 comma b, and that's also stretching by a factor of b. Of course, if b is less than 1 in absolute value, then it's not a stretching, it's compression. Anyway, here's a visualization. This program is randomized, so if I run again, I'll get different AB value. Here A is 1.47 something, nearly 1.5, and B is 1.77, so stretch by about 1.5, stretching by about 1.77, so stretch a bit further in Y direction, in E2 direction. Consequently, this circle is a little bit more elongated in vertical direction. Let's run this again. This time A is about 1.019 something, so pretty close to the original, but this is compression in vertical direction. In E2 direction, it's a compression. 0.74 something, pretty close to about 3/4. And as you can see, we have ellipse, which is elongated in horizontal direction, or crushed, contracted in vertical direction. So you can see those simply by looking at the image of those, image of those basis vectors. 1, 0 is going where, 0, 1 is going where. How about the next example? Well, f is sending 1, 0 to what? What's the first column? First column is 0, 1, isn't it? 0, 1. And then E2, 0, 1 is going to the second column, 1, 0. So basically, E1 is going to E2, and E2 is going to E1. So we are switching horizontal and vertical. Here's a visualization. Blue is E1, and then blue sent to vertical. Red is E2, and that's sent to horizontal. Basically, we switched X and Y coordinates, E1 and E2, X direction and Y direction. And that's equivalent to flipping with respect to the diagonal, X equals to Y, as you can see in this picture. And you've done it before when you discussed those inverse functions and graphs of inverse functions way back in college algebra. Here's the next example. E1 is going to cosine of theta, sine of theta. E2 is going to negative sine of theta, cosine of theta. That's basically it. Sorry about that. Okay, 1, 0 is being sent to where? Cosine of theta, comma sine of theta. And zero, 1, E2 is 0, 1, is sent to where? negative sine of theta, cosine of theta. What is this? As you can see, it's a rotation. Here, this program is randomized, and theta is negative 0.47 pi, so nearly negative 90 degrees, nearly half, so negative half pi, so negative 90 degrees, so nearly 90 degrees clockwise. So blue is, okay, get the cosine of theta, sine of theta, and then started from here, and the negative sine of theta, comma cosine of theta. Let's run it again. This time, a little bit more than 0.5 pi, so a little bit more than 90 degree rotation, and so on and so forth. So you can see these effects by simply looking at where do those basis vectors are going. 1, 0 is going to cosine, comma sine, and 0, 1 is going to negative sine theta, comma cosine of theta. Okay, so much for section 2 of this notebook. We have a little bit of time left, so let's have a brief review again. Let's suppose we have vectors v and w with basis v1, v2, v3 all the way up to vn, and w1, w2, w3 all the way to wm. Now, if we have set bases, then each vector will have unique coordinate expression. If we have different spaces, then the same vector will have different coordinate expressions, so we should not be changing the basis. Most of the time, it's a good idea to stay with the standard basis vectors, e1, e2, e3 all the way to en for Rn, and for Rm goes to em. But in general, we have v1, v2 all the way up to vn, and w1, w2, w3 all the way up to wm. So n-dimensional going to m-dimensional. And what do we do? L of v1, L of v2, L of v3, and so on and so forth will go to columns, columns, columns. And that's how you get the matrix expression. Examples like these. Okay, this is typical example. E1 is going to 1, 1, 2. E2 is going to negative 1, 3, 4. And arrange them in columns. And that's the matrix associated to this linear map. In general, we have this kind of expression. Column, 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 dot, 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 all the way to column. And we went through the proof as well. It was tricky and a bit tedious, but please remember the end result, everybody.